Hi everyone. So we're going to jump into linked lists just to make sure we have more examples of what we can do with structures, arrays, pointers, that sort of thing. Basic C code. And then we're going to revisit linked lists when we deal with objects. We're going to revisit it again when we deal with more elaborate objects, when we deal with polymorphism, when we deal with inheritance. We're going to be dealing with it again when we deal with just templated classes. We're going to keep on using it again and again to try and motivate why we're learning different topics so that you're not learning new code and new structures each and every time. We're going to use this as the guiding example. So here is the idea of a linked list. Now you can come up with all sorts of metaphors, ducks swimming together, that sort of thing. So how do ducks follow a pattern? You go in a line, for example. Well, one leads, the other one, next one follows the one in front of it, the one follows after that one. They're not following the lead duck, they're following whatever duck was immediately in front of them. Conga line, same idea. This is what we're talking about when it comes to a linked list. So we're going to look at what one is, how do they work, how do we implement it, and then we're going to hopefully I'm going to live code it and not make a whole lot of mistakes. I will say it's going to be live coding and I could make mistakes, and that's sort of the point. If I make a mistake somewhere along the lines, I want to see the actual process in action, not just, and including how I debug my code, not just, oh, hey, this is a perfectly done example. If I just gave you the code and it was working and it was perfect and it was clean, we don't go through some of the more important process of how we overcome some of this adversity or how we overcome some of the problems we hit. So the live coding, it's designed, even if I'm recording it, it's designed to show you how I work through a problem. Okay, so this is, I like the train metaphor instead. This is Canada's, and I think maybe the world's for a little while, but it was Canada's longest train in history. It was a grain train in Canada, has two different engines and a slew of grain cars behind it. Anyone that's lived on the prairies probably knows, has seen this sort of thing. Heck, you'll even see these in Ontario from time to time. When you wait at a railroad crossing, you see the train and you go, oh my god, this just keeps on going. Like a passenger train is like 10 cars. Some of these grain trains are, 100 cars, one after the other. They can be extraordinarily long. Why? Why do trains work? That's not meant to be a philosophical question, but we're going to do something very similar to that. Much like a train, if I need to add another I just add it to the back or add it in the middle somehow, but decouple two of the cars, put something in the middle, couple them back up again. Instead of knowing I have one gigantic array, what if I consider each part one after the other, and the only important part for this car right here, it matters what's in front of it, not even what's behind it, and this car matters what's in front of it. It just connects to the car in front of it. So if I want to go down my train, I can go from the back all the way up and just keep on following the next, the next, the next, the next, until I get to the front of the train. That is what we're dealing with a linked list. It is not a set size. You just keep on adding carts to it until however many you need. And if you need to put something in, you just decouple it, put something in, and then you're back with this whole conga line approach. This string of data items, one after the other. It's very useful when I don't know how big something is going to be. So let's take, we could take a barbershop, but I like taking a hospital visit. So if I'm going to go to the emergency room, you normally form a line, right? Or some kind of queue. You're waiting for your number to come up. If someone comes in with a missing arm and it's still bleeding, they're going to the front of the line. You may have the sniffles, you may have stubbed your toe, or whatever the case is, but that person's going straight to the front of the line. Or maybe somebody has to go back to work, so they're waiting in the line and then they leave. At no point in time, if I had an array, what do I need to, and let's say I put down chairs for people waiting in line. That would be like an array. I have a set of chairs, one after the other, and when I go to the hospital, I sit down in one chair, and when the next person's called, what do you need to do? So what the person at the very front leaves, and what does everyone have to do? They all have to stand up, shift over one chair, sit back down. That's a big pain in the ass, right? No one wants to do that. Just every time someone moves, everyone stands up, moves over, sits back down. Somebody comes in with a missing arm, everyone has to shift back the other direction. That's not what we ideally want. At a barber shop, I'm going to do something slightly different. Barbershops, if for those of you that have, or I don't think hair salons have the same issue. Barbershops are, or I find it a little bit stressful, but you wait around, or at least the barbershops I go to, you wait around and you sort of monitor who was there just before you or who came in after you. But really, you only need to know who is before you in line. Irrespective of how many people are there, you just need to know who's in front of you in line. One person. And when they go up, you know you're next. That's a linked list. Instead of having to have these set number of chairs, and oh, by the way, if you're at the emergency room and you have one extra person show up, you need to find another chair and put it down, right? Or you need to readjust things. If you don't have enough spaces in the waiting room, you may have to relay out all the chairs all over again. If I have variable sizes or if I'm removing or adding items to an array, it can be a very costly operation. So instead, what I want to do in some of these cases are I just want to know who's in front of me, and there's somebody at the head of the line, the person behind them knows exactly who's in front of them, the person behind them knows exactly who's in front of them. You just need to know who's in front of you, and that's all you need. You don't have to make an array. You don't have to call malloc or new. You don't have to make a brand new data structure. And if I never run out of space because I just can add more people to the line. Here's what a linked list would look like. So I have a linked list. Each one of these things is a node. We'll call these a node. So let's put the word node in there. A linked list node. We could call it some other name, but let's call it a node. It will have wrapped up in it, it will have its data, and it will have what is next, the next node in my linked list. Much like a train. The train has a cart, right? It has some wheels, fine. But it has the data and it has what it's connected to, the next thing in the train, and so forth and so on. How do I know when I get to the end? I get to the end when there's no more trains attached. There's no more train cars attached. That's it. I just need to keep on making new ones of these, and I need to hook it up to the one before it, and once I've done that, I'm fine. And if I remove or add items, it doesn't really matter. It's fine. And this is what we're going to be dealing with a linked list. It becomes a lot more powerful once you actually get to objects, because once you get to objects, now the ability to make these nodes and not have to worry about them accidentally being deleted or destroyed, that's a different, it handles itself. So that's what we're doing with a linked list. We have we have the very first element in my linked list, and then that connects to the next one, which connects to the next one, which connects to the next one, all the way up until I get it's connecting to nothing else. That's when I stop. That's it. There's nothing weird about it. The data could be any kind of data that you want. We're going to implement it with, let's implement it with an integer, but it could be with a text string, it could be with a student structure, it could be anything in there. Okay. If I want to add an element, it depends on where I want to add it. I can either add it to the very front of my list, I can add it to the very back of my list, or maybe I want to add it in the middle. Let's add it in the middle. So here's what I'm going to do. I'm going to add it right there. So I need to connect this data item here. I want to connect this data item here to this one here, and then and only then do I connect this to this so that I don't break the chain. I need to be, otherwise I won't know where this one is. If I break up this chain right here, if I kill this connection here, I won't know where this thing is anymore. I have the start, I can find where this connection is. I need to then add this to this and this to that afterwards. So I theoretically or conceptually move it apart. I hook up this to this. So I have two things pointing to this data item, this node. I have this is pointing to this node, and this is pointing to this node. And they are pointers. Let's be very clear about this. This is why we need to know pointers so well. I'm pointing to the other node. And once I've done this, and I have two pointers to the same node, I can get rid of this pointer here, and hook it up to here. And now I have extended my linked list by one. I have inserted a new element. And depending on how I want to do it, I could have sorted linked lists. I can always add to the end. I can always add to the front. It doesn't really matter. The act of finding where to add it is actually more costly than the act of inserting something. Unlike an array where I may have to copy everything over to another array. Yes, if I run out of space within an array, I have to copy everything over to a bigger array and then delete my original array. This is, I just add new nodes. The ability to find where I add the new node, that takes time. So adding an element's cheap. There's only 2 pointer changes needed. The finding where to insert it or finding things in the array, I cannot just jump to position 2, right? I can't go, oh, I'm going to go to position 2 here and just jump here. For a linked list, I need to find the second position. Okay, 0, 1, 2. I have to walk down my linked list to find a particular element. If I want the fifth element, 0, 1, 2, 3, 4. Oh, there's no fifth element. I got to walk down my linked list. If I want the size of my linked list, I got to walk down the linked list counting how many nodes I have. There are ways of speeding some of this up, but not really. It is a time intensive process. So, inserting is a pain. That's the problem with the linked list, and you can accidentally uncouple things. But they are ubiquitous. They're found all sorts of different places. Heck, we'll reuse linked lists when we deal with stacks and queues later on in the term, and you won't even need to know. So here's the linked list functions I'm going to be dealing with. I'm going to have insert at the front. I'm going to have insert at the back. I may have remove at the front. I'm going to also change. Oh no, I'm passing in the linked list structure. Okay. Remove from the back, remove from the front, checking out if the linked list is empty, and then maybe printing off my linked list. So I need to figure out how I'm going to do this. So first of all, I would break up my piece of paper and I'd play around with how I would expect this thing to work. And I'd doodle out those little squares and how they're linked up and just get a sense of how they all work. We're going to actually code this up, but I need to figure out what a linked list is. And it's not the node itself because I want to pass off the entire linked list and essentially or invariably the start of my linked list. And then after I pass off the start of the linked list, and then I can follow the nodes one after the other to the next part. So here is what I'm going to do. Here's at least my thought. That thing here is then going to point to let's put a star in there. It's going to point to my starting node of my linked list, which then essentially this will be a pointer to the start. The start of my linked list is here, then points to here, this points to here. And then it gets to the empty. Okay, so I'm going to keep on passing around this thing here, which allows me to then walk down my entire linked list. But this is the pointer to this thing here. Or I can say I'm pointing to this thing here. Let's just get rid of this thing altogether. I'm pointing to the very first node of my linked list. And so if I want to find out if it's empty, what do? I check to see if I'm pointing to something. If I'm pointing to a linked list node, it's not empty. Done. I don't even need to count it. I could get the size. I could have a function for getting the size. Let's say I had to do the print one. I start with this linked list node. I check to see if I have a pointer to the start. If I do, then I go to the start, then I go to the next, then I go to the next, and for each one of these things, I print off something about the linked list. If I want to remove from the front, what will I need to do? I will see if there's a front. If there's a front, I go to the front, check if there's a next. If there's a next, hook up this to this and remove this element. So I would need to go past and then go back. Removing from the back, I would have to walk down my list, get to the second last element, remove this, and become null. So I'd walk down, I get to the second last element, so I check to see if the next one is connected, if it's empty, or if it's connected to something else. And if this is connected to nothing else, then I'm going to connect this to nothing, essentially. If I need to insert at the front, what do? I'm going to make a new node, plop it down here, couple this to this new node, and then I'm good to go. Oh, and then hook this new node to this. I want to play with all of these ideas one after the other to make sure that they all work. Okay, so inserting at the front, here's my first pointer, right? Or the start of my linked list node. It's pointing to the 7. So if I'm going to insert so I'm making a new pointer. So this is the data, and it's pointing to nothing afterwards. I am then going to connect this thing up to the 7, and then connect my linked list up to the new pointer. Oh, and then point to this thing here. These are just pointers. So this is a pointer to, this is the data structure I'm actually storing. So this, the first pointer would then point to this, and then this next would point to this, which is what I have here. If I'm inserting at the back, well, I need to, that's removed from the back. So let's insert it from the back. So linked list node. Let's see what numbers we had. 7 and 11. And let's do the new one. 12, 7, and 11. So let's also erase it. No, that's wrong button. So I know that it's an empty list if I'm not pointing to anything. I have a null pointer here. This thing is just going to point to this next part here. So to insert at, I'm going to insert at the back, sorry, not delete at the back. Let's insert a brand new node pointer to, let's say 13, and then nothing. Okay, so what do I need to do? I need to start at the front. I keep walking down until I get to one that has nothing at the end, and then I'm going to hook this thing. Control Z. Does that work? No, it doesn't. I am then going to, let's delete this. I'm then going to plug the point to this thing here, and then this thing is still pointing to nothing. So I walk down my array, I get to the end, and then hook it up to the next element. If I want to remove from the front, what do I need to do? Well, I have the pointer to the very front, so instead I point it to the next element, then I can just delete this thing, or just leave it alone. Okay, sometimes I may have to delete it, or I can just, ignore it. So I have my first pointer, I point it to the new thing, I have a temp pointer pointing to this, and if I need to delete this, I can delete that. So this is what our basic idea is. We have a bunch of nodes, we have something that points to the first of those nodes. We can insert at the beginning, the middle, or the end if we want. We can remove from the beginning, middle, and end. We can search for individual things. Heck, we can even do other kinds of linked list nodes, like doubly linked list nodes, so you can get the previous and the next. So you can go forward and back in a linked list. Or we can have circular linked lists. So when you get to the end, you just point to the very first element again. In that case, you need to have a count for how many linked list elements you have. It just comes up over and over again in other places. So let's code this thing up. So let's just go, here's my old function for min factor. I'm going to make a new project. Hopefully it's still going to be in the same position in class code. L03 linked list demo. So I'm going to make a brand new CPP file. Notice we're doing just C code, but it is, it doesn't really matter. It doesn't matter if it's C or C++. They're always just .cpp for Visual Studio. Okay, do I want standard I/O? I think I'm going to need it. So include, and then I'm going to include, because I know myself by now, and I know I'm going to use asserts because I'm anal retentive that way. Okay, struct, and then I'm going to call it LL node. I could capitalize it if I wanted to, depending on how I want to do it. LL node, let's do it that way. And what's in a linked list node? Well, this is where it might get a little wonky. So int, call it data. The data is just going to be a type of integer right now. It could be anything. It could be strings. It could be another structure. I could have, let's do that. Struct ll data, and that is int num or something like that. Okay, so we're going to throw in ll data instead. Why not? And if I wanted to make it strings, I would just change it here, and nothing would change. Okay, I'm going to make a brand new struct, call linked list. Linked list. And then what's this going to have? It's going to have, oh, I didn't finish this up. So I have a data structure, fine. I'm also going to have something else. I need the pointer to the next. So ll node, and then next. I put a P to say, hey, it's a pointer to a linked list node. After that, what am I going to do? I'm going to, for my linked list itself, all I need is a start. LL node, and I could put the star there, P start. Right? It's a start to, and this is going to point to this one. This will point to another one, which will point to another one, which will point to another one. So, what did I want for my functions? So I'm going to need a main method, and I'm also going to get my linked list node. Accidentally click something here. I have a bunch of different function names, so I want to see what function names I want to have. I'm going to define these functions. I could define other functions as well. I'm just going to be lazy and just, and I'm going to have to rename some of these things. These are going to be my prototypes. Okay. And there we go. So we're going to have a data type. We could call it my data if I wanted to. In case you're wondering what the heck this const means, it means I'm not allowed to modify this variable once it comes in. I pass in this variable and it cannot be changed. This function is not allowed to change anything. I cannot modify my linked list when I do use this kind of thing. And so the idea here is I can make certain guarantees about how things are going to work. If I'm printing off of my linked list, I don't need to worry about changing anything. I don't need to worry about this. So if I'm printing off my linked list, I'm not going to change any of my data structures. So therefore, I'm not allowed to change anything. Okay. Notice this linked list will all it is pointing to something. So if I make a brand new linked list and point to the same thing, I don't have to worry about passing a pointer of type linked list. We'll get to that in a second, but these should be all of our different basic prototypes. We'll also add other stuff, but this is what we're going to play around with. Okay, next I'm going to also need a whole bunch of other helper functions in there as well. So int main, and we're going to make a bunch of linked lists. Linked list ll. So we're going to make a linked list, and then we're going to insert at front, and let's see here. I'm going to put my LL in here. It's going to make a copy of it, but it's just going to point to the front. Um, and insert at front. Actually, I do need to modify some stuff. The linked list itself is going to make a duplicate of this linked list, and I'm going to need to modify it afterwards. So I can either pass off that linked list again, which I probably should do. Oh, I don't want to remove from the front, remove the back. Okay, let's just put a pointer. PLL. And if I want to be consistent, I could just do that. So why do I want a pointer here? Because if I pass in just the linked list itself, I will make a brand new linked list, copy all the data over, the values for that linked list, copy it over to this brand new linked list, and if I modify this linked list here as a parameter, it doesn't affect the original. So if I pass in a pointer to a linked list, then it means that I will be modifying the original data that I had. Remember we talked about I only pass values, I don't pass the variable itself. And so if I pass a pointer to that variable itself, I can modify the variable, the original variable. All right, and it's going to be a pointer to my linked list. And I'm going to insert my data, so I need something like a new kind of data. So let's make this data1 dot number is equal to 2. Let's make a bunch of these. 2, data 3, data 4, data 5. All right, make a brand new bunch of numbers. And I'm going to change 2, 3, 4, 5. Okay, and I'm going to put some numbers in here 2, 3, 4, 5, 6. We could probably just, we could change it around if you wanted. Let's do -2, 17. So we don't have the numbers and confusing the data 3 with the values that's being stored. I already did 17, 21, and 0. Okay, I'm going to insert at the front. I'm going to insert data 1. Okay, I'm going to insert at the front data 2. So what's going to happen if I insert data 2 after data 1? It means the order in my linked list will be data 2, then data 1, the data 1 node afterwards. So I would expect to see, in terms of the numbers being stored, 17 and then a -2 afterwards. I'm going to insert at back data 3. Let's do that a bunch for times. 4, 5. Okay, so I'm going to insert a bunch of data. Then I'm going to remove from the back and linked list. And then I'm going to remove from front. And I'm going to remove my very first element. And let's print my linked list. What's it called? What did I call it? Do I have linked list print or something like that? Oh, it's called print is empty linked list. Let's call it that. Okay, so I'm going to print my linked list at 11 LL. All right, so I'm going to print my linked list. I'm going to remove 2 elements. I'm going to print my linked list again just to see what happens. Okay, that's all I've done. I can technically try and compile. It's not going to work, but I can try and compile. It says I haven't not allowed to modify non-member functions. Is empty linked list. Let's get rid of. It's not allowed to modify non-member functions, and I can't guarantee that. I think with this, If I get rid of that, then I'm fine. Print LL. Okay, is empty. Let's see, is empty at the beginning before I do something. Is empty linked list, and this is going to be just my linked list. I'm going to add a bunch of stuff, and I want to make sure that, let's put that assert, and I'm going to say it's not that. So I'm asserting that this is not empty after I've done all this, and I'm going to say I'm going to assert it is empty before I do anything. That's fairly safe, right? I make a new linked list, I didn't add anything, it should be empty. I don't, if I've added a bunch of stuff, and then it should no longer be empty. That's what the not is here. It is not empty. Is empty is going to be return false. Not that means it's true. I'm asserting that it must be true. Then I'm going to remove a couple nodes. I'm going to print it off again. Okay, still don't have anything. So let's build this and see what happens. Allowed a number. This might be an object thing, so let's just get rid of it for now. Constants on a function, we definitely will put those in later, but for C code, maybe that doesn't work. So let's have a look. Okay, so notice I'm going to uninitialize variable linked list used. Okay, I didn't initialize my linked list. Okay, let's do that. These are the sorts of things I want to hit right away. So ll dot pstart, and what do I want the pstart to be equal to? It should be equal to null. Remember, when I make a linked list, if I have a pointer to something, I either need it to point to something legitimate or to point to null. So when I hit an uninitialized variable, I want to deal with that. I want to set what I'm pointing to null. It's an empty linked list. So what I expect here is when I call, where is it now? Is empty linked list, I check to see if pstart is equal to null. If it is, return true, right? And when I print it, I check to see, hey, by the way, do I have any elements in there? This is one of those things I can do over and over again. Okay, so let's do the next set of functions. So here's what we're going to do. I've done a bunch of this stuff, and I'll probably need a whole lot more functions in a second. Anytime I have a function that it's going to be, maybe that would be useful, or I'm going to need to do that a whole bunch of times, I'm going to make a function for it. Why? Because it might be useful. Okay, so is empty. I'm going to check to see if, and it shouldn't be a PLL, it should just be LL, because I don't no longer have it's no longer a pointer. I could do a pointer if I wanted to be consistent, but I'm definitely not modifying this linked list. Okay, so I want to see if this thing is empty. I will have a linked list. What I can say is return, because all I'm going to check to see is if the start is empty or not. Return ll dot, that's it, right? Is the start pointing to null? If it's pointing to null, I have an empty linked list. I have no nodes. That's it. Okay. What I could do here is just keep on asking, hey, by the way, is this empty or not? So if is empty ll, because I don't want to be doing this thing each time. I wrote the function to check to see if it's empty one time, and I want to keep on using it because I don't want to do it the one way. If I change my code, I would only need to change it in one place. If it's empty, and then I'm going to do printf the list is empty, and then maybe a /n. All right, otherwise, what am I going to do? I'm going to take the first node, I'm going to walk down each one of my nodes, So I probably need a while loop on this one. I'm going to go from each node, node after node, walking down my linked list and printing off the contents. Okay, so so I want to see what the heck this structure I have is called again. The structure called an LL node. The current node. I like abbreviations. So here is my current node. It's going to be equal to ll.pstart. Great. That's my current node, the start node. While, and then I can check to see if p cur node. Okay, I could always make it while p cur node does not equal to null. Now, for any of you that have done coding with me before, you know I get really lazy with this sort of thing. I will often, instead of doing this, null is the others is 0, and if it's not null, it's not 0. Anything that a true or false statement is either true, as in not 0, or false, which is 0. Essentially, I can do this. It's the exact same thing. While cur node, if it's a null pointer, it stops, means it's null is false is equivalent to false. Otherwise, it keeps on being true. Okay, while cur node. Okay, so which I can say, let's put it as a comment. Does not equal null. All right, there we go. Next up, I want to print off information about that node. So maybe I might want a function to do that. So let's do that. So void print node and ll node. It's going to take a pointer to a node. It's going to print out information about that node and then be done with it. So I could put this up in my prototypes if I wanted to as well. So let's actually do that just for consistency's sake. Let's pop that at the top. Something about helper functions, main linked list functions. All right, and here are my main functions. I'm going to put all my helper functions, the things that are going to help me along my way, up there. The assert is going to be, there's something wrong with this assert. What's going on here? Is empty linked list. Oh, is empty linked list should be actually defined. Let's must return a value. True. Why? I'm just going to put something to make it compile while I'm doing this, and we'll go back to it later. Or I can keep on having it break on me, but that's fine. All right. So what am I doing here? For each one of these nodes, I'm going to print the node called print node on p cur node, and then I'm going to say p cur node is equal to p cur node. And remember, normally we get a member variable by putting a dot, right? Except it's not. It might actually let us do that, but really we shouldn't be doing that. Well, you'll see it. Hopefully, should automatically change. For a structure, normally you put a dot, but we're talking about a pointer to a structure. So if I put a dot and press enter, look what I get. If I'm dealing with a pointer to a structure, I use an arrow. It's a dash and closing angled parentheses, but it's an arrow. That's the equivalent of a point. So if I'm dealing with a struct, I normally use a dot. Otherwise, instead of a dot, I use an arrow instead for when I'm dealing with a pointer to a structure. We're going to see this again and again and again. All right, so I'm just going to get the next node. And then I can keep on looping around and assuming that at some point in time, the current node is going to be, the next is going to be a null at some point in time, and then I'm going to stop. So print node, all this is going to say is Let's do printf, and let's do n, and I'm going to put a percent I. So I'm going to take some integer. I can put a decimal. That's probably the more standardized approach. P node. I'm going to use my arrow directly this time. The kind of data that I have. And then what else do I need? So this is going to be a kind of data, and then the number. So I'm just going to put n and then a number, n and a number. Let's put a dash afterwards as well, or a tilde, just so it looks like we have a nice formatted thing. Then I'm going to I need to figure out something else. Oh wait, what if p node is null? That's going to be, if I pass in a null here, I want to look at this thing and go like, what if I pass in a null? If I pass in a null, I can't get the data for a null pointer. I'll get a null pointer exception if I try and do this, if p node is null. So instead I say if p node, I can put it right in there, or I can handle the error message somehow. Let's handle the error message. Or I could do this. Let's do it a different way. Assert p node. I'm assuming that I don't have a null pointer. If I do, crash and tell me exactly where I crashed. It can be useful. Or I could just handle it with an if statement as well. That both would work. So this is me printing off information about an individual node. This goes through each individual node, and then calls print node for each individual node until I get to p cur node not being equal to null. When I get to the end of my linked list, then I stop. I need a semicolon here because I have an underline here. Okay, and I can check to see if something is empty. Great. So far, so good. This so far is going to do absolutely nothing. But I can check my code and it's going to crash, but I can check my code. Right? It's compiling. Let's see what happens. It should hopefully crash. All right, we're going to retry. Let's see where we have. Hey, we're asserting that our linked list node is empty. It is after doing all these inserts. It goes past the first one. The linked list node at the start is empty. Great, it blows up. And after I've done a bunch of inserts and I call the print ll on it, then I crash because it's still empty. I've tried to add a bunch of elements and nothing got added. I didn't do the insert at back or insert at front yet. This is where asserts would tell me what happened, right? It's ll, and then I could go into it and, oh wait, the p start, it points to null. Okay, so insert at back, insert at front. So let's do insert at front. So I have a linked list node. I want to check to see if p ll, and then I need the start. If I already have a start, then I need to do something else. I need to keep around what my previous start was. So I'm going to also make a new node, and then I need to make sure I keep that node around. That's going to be a problem. So here's what my issue is going to be. I am going to be making all these linked list nodes. Every time I make a new node in here, if I make a new node in here, it gets deleted as soon as I get to the bottom. As soon as I'm done with my linked list nodes, it's going to just get rid of it all. So unless I dynamically create a linked list node and keep on keeping that around and then going back afterwards and cleaning it all up, this is going to lead to a problem. So I could, let me see here. So I want to think about what my approach is, but the problem is going to be if I call ll node to add, right? If I make a new node called llnode.toAdd, and then I add it to my linked list, when I get done with this function, what's going to happen to add node? Variables live and die within my function. At the end of that function, this thing is going to get deleted. So all this hard work I'm going to do, I'm going to add it, it's going to point to something, and then the thing it's pointing to is just going to magically disappear. I need to permanently keep around some kind of linked list node. So although this is going to be a bit hacky and ugly, we need some clean way of making a new node that is not going to just automatically be deleted afterwards. Okay, so I made all these data, all this data. Maybe what I need to do is node and node 1, and what I should do is make a whole bunch of linked list nodes. So let me think of the best way of doing this. I could add the data itself. It will make a brand new linked list node, add it to my linked list. But if I do that, it's going to be deleted immediately afterwards. I could call malloc or something like that, make that new data type, and pass it. So I can call malloc on a single element, and then after all is said and done, when I'm finally done with my program, and let's do that. Let's do it that way, actually. So instead of an array, I'm going to get essentially an array of exactly one element. Is equal to ll node star malloc size of, so size of ll node multiplied by 1. It's exactly one element. I'm going to make a single element malloc. I'm going to say to add node, and then I'm going to, the data is going to be equal to, I'm going to copy that data over to add. So I'm just going to copy that over, the data over to this thing here, the whole thing. And then I'm also going to say to add node is, and then the next is equal to null. And then you might realize that I may have a, not a problem, but maybe I don't want to do this each and every time. Maybe I just want to say make a new node, linked list node based on some data type. So I pass in the data, I make a brand new linked list node. So I'm going to do that because I'm going to also have to do that at insert it back as well. So I'm going to have something called ll node, and then it's going to say make node. It's going to take in a constant ll data to add, and all this thing is going to do is it's going to do all of this stuff instead right here, return to add node. So I'm going to make a brand new node, add my data, make the pointer point to null, return that node, the pointer to that node itself. And so I can say make node to add, and then I'm going to have ll node. All right, so I'm going to make a brand new linked list node. If there's not, so I'm going to make that node no matter what. I'm also going to have to do this, insert it back here as well. When I make a brand new node, I'm going to make it in both those cases based on the data. So I am then going to figure out if I have an empty linked list. If I don't have an empty linked list, I need to update where this thing is pointing. Otherwise, I'm going to just make p start, p ll, p start. I need to make that point to add node. All right. So it will then point to this linked list node. No matter what, it's going to point to that. The start is going to always point to this new node that I've just added. But if there was already a start, I need to say to add node and set the next to be equal to p ll p start. All right. What's this doing? This is going to update. I make a brand new node. I am then pointing the next to what the original start was. And then I point my linked list to point to this new node that I have. So I'm inserting it at the front of my linked list. Okay, let's do the insert at the back. So that should actually do it for me. And I don't return anything. I'm adding this value. I have a pointer to this. That should work just fine. Okay, let's check the inserting at the back. I'm going to make a brand new node. I'm going to have to check to see if PLL P start is equal to null again. Because if it's not equal to null, I need to get the very last node in my linked list, and then I need to, or I could do one of two ways, but I need to get the very last node in my linked list and then insert it after that. So and the to add node is not going to change at all. Okay, so I need something to test if I get the last element in my list. Okay, maybe I want some. Let's do it the slow way first for right now, and then see what we get. So while and I want to stop when they. So I'm going to have something called pcur, like I had last time. LL node pcur node. Okay, is equal to p. Oh, p. While and let's see if there's something else wrong. What's that? What's wrong with this? Oh, I need a pointer. Great. So I'm going to make a current node. I'm going to make it to whatever the starter node is, and then I'm going to keep on saying, well, pcur node dot next does not equal null, or I can just say if it's equal to that. Then I'm going to just keep on pcur node. I'm going to get the next, and then that p. There we go. I'm going to just point to the next one, point to the next one. I'm going to. This is going to walk down the linked. All right. So I'm going to start at the start and walk down my linked list until I get to the very end. Maybe you might notice some kind of weird quirk in this. Oh, actually, no, it's covered. If there's no starting point, if I have no start, then I don't do this at all. If I do have a start, then I get the start, make it the current node, walk down until it's an empty linked list, until it's the last node. That'll be my new current. And then if once I get to that point, then I need to p current node p next is equal to add node. Instead of it being pointing to null, I'm going to point to this new node I'm going to add. The new node I'm going to add points to null at the end. It is my new final node. So I walk down to the very end of my list, and I just attach the new node that I just created to the very end, to p next. Once I'm all done, if I don't have a start, then else I need an else statement, because if I don't have a starting point, what do I need to do? I need to make PLL equal to P start. I need to make that equal to add node. Notice I'm being very inconsistent, so let's remove my inconsistency. P add node. It's a pointer to a linked list node, so I should put a p in underscore if I'm going to be consistent. All right. So if I have anything on my list, I walk to the end of my list, add it to the end. If there's nothing in my list, I need to add it to the very front because there's nothing else in my list, and so I add it there. Let's remove it from the front. So I have a node that I want to remove from the front. I need to if p l. Let's figure out if this is empty. is empty LL P, and this is going to dereference it. If there's nothing in my list, stop. I'm going to do that down here as well. Okay. Otherwise, what do I need to do? The other condition, so if I don't go into this, if I go into this if statement, I'm going to bail out of my program. Or get out of my function. Otherwise, I'm assuming it's not empty, and now I need to figure out how to remove it from the very front. If it's not empty, I know there's a first element, and so I need to figure out what if there's a next element. So P. Let's actually just do it as an if statement or an else if. So I know that they have to have a start there. If P start, if that is not null, then I need to save that up. Oh, what I could do is instead of this is this. So P my next node, I'm going to keep that around no matter what. If there's nothing after the first node, it's null. If there's something after it, then it's this new node. Who cares? Because what I'm going to now do is I'm going to say P LL P start is equal to P next. Whether it's null or not, it doesn't matter. If I only have one element, I've destroyed that element. Otherwise, I do this. Now, you'll notice something else weird about this. I might need to del. I will need to get rid of this. So, and then I'm going to say P start to del. If I'm deleting that node from my list, I just remove it from the front, and but I have to delete that node. I've called malloc. I got to call free. Okay, the other option, and I don't know how that's going to work here. So if I'm going to remove it from the back, I need to find the last element in my array. It's going to do exactly the same thing as this. I'm going to get the last element of my array. I need to get the second last element of my array, actually. So I get the second last element of my array, and then I delete the last element. But so it's going to look very similar to this. Remove from back. Okay, so if my linked list is empty, then I just return false. Oh, I need to return true, by the way. Otherwise, if I only have one element in my list, I need to figure out if I have multiple elements. So I'm going to start here. I'm going to start at the start. As soon as I have, if the p next is, if I don't have a next element, then I'm at the last element. If and then I would need that one element before that. So let's see how I want to do this. I'm going to walk down my list one at a time, and I break up my piece of paper for this. I'm going to walk down my linked list one at a time. When I get to the second last element, I'm going to stop. I can only know if I'm at the second last element if I check if the next has a next. Okay. So I walk down my linked list and I check to see if the next to the next p cur node p next is equal to null. That's the second last element, right? The next to the next is null. If that's the case, I'm going to remove the element afterwards. Otherwise, I keep going. Okay, so I have a starting point. I want to see if p cur node. I want to see if I only have one node to begin with. So I want to see if p next is equal to null. If I only have a single element, I'm in trouble. I just want to get rid of everything. I also know that the start element, or I can just see if the p start is equal to the starting element is equal to null. Might be easier to get our heads around. So let's move it around a little bit. Okay, so I check to see if the start element is if I have a list of only exactly one element. That's what this is. So we're going to move this down. We're going to go up here. All right, we'll link list with exactly one element. That's what we're looking for. In that case, I know that I need to change what my p start is going to be. I'm going to also delete what my node originally was. So I'm going to p start. I'm going to free p start, and then I'm also going to p start is equal to null. Okay, if I have one element, I delete it. Otherwise, I need to walk down my list. I know that I have more than one element in there. So if I have p next, if I have a next of a next, I know I can't have just only a single next. So if I have a next to next, and as long as that's not equal to null, I keep on going to the next one. The second last. So I'm going to start at the start, walk my way down until I'm at the second last element. That's what this thing is saying. As long as it's not the second last element. So at the last element, p next would be null. The second last element, the next of the next would be null. That's how you know it's the second last element. So when I get to the second last element, that's when I want to start. Otherwise, I'm going to just keep on going one further down as I go. Okay. So p next in this case is going to be the last element. So I want to store this around. So p2del. I want to store the thing I'm going to be deleting eventually. I'm going to say p current node p next is equal to null, or I could have done it actually in the other order. I could just free it and then delete it. That also works. And then I'm going to say free p 2del. And in those cases, I'm going to return true. And this is going to be return true. I deleted an element. Good to go. Third option, there is no elements to delete, so I don't delete that element. I checked out this. I'm checking out this. Okay. Let's compile it. Let's see what happens. Oh, I have a semicolon missing somewhere. Oh, there it is. The line above. Right. Let's try it again. I don't even try and do a bunch of other things at once. This might be the Google. Yeah, this is a Google thing. Since it's syncing up to my Google Drive, I sometimes get little synchronization issues. Okay. Everything compiles. Everything's A-OK. Let's check it out. And we're going to find out the hard way if this thing actually works. So what could I do? I could get to here and put a breakpoint. But you'll notice I'm also putting a print statement anyways in here. I'm printing out my linked list in any event. So I don't need to necessarily do anything. I could just see if this prints out okay. I'm going to put a breakpoint here just to stop things when I get there. Okay, let's see what my thing says. N17, N-2, N9, N21, N0. Let's see what this thing should say. I'm inserting at the front. I'm inserting the value. Let's see here. -2, I'm inserting at the front. Then I'm inserting in front of that the 17. That's what data 2 is going to do. Then I'm inserting at the back. I'm going to insert 9. Then I'm going to insert 21. Then I'm going to insert 0. What I expect is 17, -2, 9, 21, 0. Let's see what I had here. 17, -2, 9, 21, 0. Great. It's actually working surprisingly. Okay, is it empty? Well, that's what crashed us last time. Let's find out if it's empty. So I'm going to, uh, let's keep those around. Let's just run the whole rest of the thing. Let's see what we have here. You'll notice I did something, well, not weird, but a slight issue with this. I have N17, N negative 2, N9, N21, N0, N negative 2, N9, N21. Wait, maybe my print statement should have a line, a carriage return afterwards, or some other information in there. So I'm going to print my linked list. The list is empty. Instead of this, what I might want to do instead is do a printf linked list, and then I'll put a space there, and I'll do a carriage return at the end to make sure that I have it on a new line no matter what. Let's see it in action again. Okay, great. It's on a new line each time. So my linked list is 17, negative 2, 9, 21, 0. Then the next thing I did with my linked list here is I inserted a bunch of stuff, I printed it off, then I removed from the back and I removed from the front. So whatever's at the very front and the very back should be removed. Let's also do a remove from the back again after remove from the back 2 more times, and then a print just again. Okay, so this is just me testing out my code to see how it works. So I'm going to remove 2 things, see what it looks like. Remove 2 more things from the back, see what it looks like. See, make sure it works as expected. And let's also close this off. Okay. So I added all those things. I removed the 17 from the front. I removed the 0 from the back. So I should get negative 2, 9, 21. Great. Then I removed 2 more things from the back, 9 and 21. So I remove the 21, then I remove the 9. I get left with n negative 2. What else might I want to do? Let's also remove 2 more times and see what happens. There's only 1 element left, right? So if I remove 2 more times, I would hopefully gracefully handle that. So if I remove the first element, it'll be removed and I'll have an empty linked list. And then I remove the other element and I should still work. And when I print off, the list is empty, nothing blew up, and it says linked list afterwards. So I'm printing my linked list is empty. I gotta look into that. Why does it say linked list at the end? Here's me printing my linked list, that's why. I finish this if statement, and then I keep on going. That's no fun. I want to, as soon as I know I have an empty linked list, I want to get out. Because otherwise I wouldn't have this linked list thing here. If I see this statement, it means I'm hitting this even with an empty list. I'm going through here and I'm going to keep on going and print off this. And I didn't want that. I want to stop when I get there. I'm also going to try something slightly different from front. I'm going to remove from the front each time just to see if that's going to blow things up. I tried it from the back. Oh, and it still works. Great. That's it. But I could keep on adding nodes to my linked list. I could add 4,000 nodes to my linked list and then print off everything in my linked list. The issue that we're going to keep having is that because we have these pointers, because we're passing around this data structure, we need to worry about the life cycle of our variables. We're going to need to worry about how we're pointing to different things, how our variables are working, how they look, what kind of what are we expecting from our functions. But at no point in time did I actually thought about this code well before I actually tried to live code it. I had a plan of attack. I know how these parts are supposed to work, and I doodled some stuff up. God knows how many times I've doodled up linked lists. The key is to think about it before you dive into your code, because if you just jump into coding things, it's going to be a terrible time for you. So make sure you think about how you want to approach this, and start coding it up in a methodical way, testing as you go, putting in comments for what the heck all this stuff means. I thought I was going to need more helper functions. I didn't, right? I could get rid of that helper function section if I wanted to, right? And just put it with the main. Let's do that. So I can what's called refactoring my code. I could, let's just delete it. I'm going to get rid of this. I'm going to put this directly above here. All right. What the heck? We just have other functions. I thought I was going to need a walking down my linked list and finding the last element as a function. Let's see what this thing here is. Dereference null pointer to add node. If this add to node is a so I should also do this. If to add node. There we go. If I'm trying to make a node, if to add node, and it should be a P. So it is barfing on me right here because of, and it should keep on barfing on me here, because you're not sure that P2 node, if malloc doesn't work right here, what's going to happen? This is going to be null, and I need to be able to handle that situation. So I have a test for it now. Great. I'm checking for errors in my code. I'm checking to see what gets underlined, that sort of thing. Okay. With that, that's a lot to cover at once. If you need to review some of these things, this code is available to you already online. If you need to re-go over parts of the video, please do so. Just keep in mind how the thought process was working. It was not just me sort of improvising everything. I had a methodical approach for how I was debugging my code, how I was thinking through my code, how I was putting an assert in certain places to make sure things were working, how I did a little bit at a time and then built from there, and how I have a data structure that I'm going to keep on going back to the rest of the term, but how it actually operates and how I think through how to process or deal with my data structure. This is by no means an easy example, but it's a realistic example for how people actually code things up. Okay, so thank you very much, everyone. And when we get back to it next time, we're going to be looking at object-oriented development. In particular, we're going to look at strings first to see what's the difference between a string and a C string. All right, thanks, everyone.